This on. All right, I think we're going to go ahead and get started with our next session on stellar evolution. We're going to hear from 4 excellent Hubble Fellows. And our first talk is going to be online from Ilva Gertberg. Ilva, are you there?
I am here. Can you hear me?
Yes.
Okay, great. Should I share the screen?
Yes, let's do that.
Okay.
And I'll give you a 2-minute warning.
Okay, excellent. Thank you. I needed to change some settings. I'm so sorry about that. Just a second.
Ilva, did we lose you?
I believe she had to close so that she could allow screen share and restart the program, so she'll be back in a minute.
Any announcements while we wait?
Okay, I'm back.
Okay.
Let's see. That should be here. You see the screen?
Yes, that looks good. So you can go ahead and take it away.
Thank you. And sorry for the delay. My name is Ylva Göthberg, and I'm a Hubble Fellow at Carnegie Observatories, and I work with interacting massive binaries. I wanted to start with saying thank you so much to the leads and for the Hubble program. It's really been very helpful for me. And I've had a lot of fun. And I'm sorry not to be there in person. I really would have wanted to, and it was my plan, but sometimes, you know, life comes in the way. So today I will tell you a little bit about the major observational and theoretical project that I've been working on for a few years now on the discovery and the properties of stars that are stripped of their hydrogen-rich envelopes through binary interaction. So what is this? What is a stripped star? This is the most common type of channel we consider, where you have 2 stars in a binary, blue because they are massive. And the most massive star, it evolves first. It swells up and fills its Roche lobe, transferring that hydrogen-rich envelope to the companion star. And left, you have that hot and compact helium core exposed. This way you can also strip stars through common envelope ejection, when instead the mass transfer it becomes unstable, the stars stay spiral closer together, and if you're lucky the envelope is ejected and you also have that helium core stripped. So what we predict for properties for these stripped stars is high effective temperatures from 50 to 100,000 Kelvin, high surface gravities of about log G of 5, and they should be hydrogen poor and helium rich on the surface, which comes from the fact that they are exposed helium cores. And if we look at the mass range of helium stars, in the low mass end we have the subdwarfs, in the high mass end we have the Wolf-Rayet stars, And I usually focus in between those. So masses roughly between 2 and 10 solar masses, something like that, for the helium core. So this comes from initial masses between maybe 5 and 30, 25 solar masses, something like that. So let's look a little bit about why I care about these stripped stars. We think that 1/3 of all hydrogen-poor supernovae actually they come from these stripped stars, because it's too many hydrogen-poor supernovae to be explained by only Wolf-Rayet stars. They also should be responsible for 2 steps in the evolution of merging binary neutron stars. So you can see how I circle here if you're familiar with the Tauris plot. And they are probably also providing quite a bit of ionizing radiation, not only hydrogen ionizing radiation, but also helium ionizing radiation. So there is some work I did on that a few years ago now on even galaxy spectra and the impact cosmologically. But talking about all of this, it's a very good question. Have you ever seen or heard about the stripped star before? What really is that? And in fact, this is really valid, because there has actually just been one object claimed, and this is this one. And I think recent work also suggests this actually is a significantly lower mass than what they were suggesting in these papers. So it has been really, really hard to find these stripped stars, which has questioned a little bit the impact of binary interaction. But as you see, binary neutron star mergers exist, and these hydrogen-poor supernovae. So I set out to try and identify a set of stripped stars and try to understand how they look like, and observationally what can we learn from them. So how to do that? This is a model of the spectral energy distribution of 4 solar mass stripped stars. So you have flux here on the y-axis and wavelength on the x-axis. And you can see that although most of that light, it is emitted in the ionizing regime where you cannot directly observe stars, there is still quite some light in the optical and the infrared and ultraviolet. So technically it shouldn't be that hard. But typically, the stripped star, it has a companion star, right? And it doesn't have to be significantly luminous bolometrically to outshine a stripped star. Here we can see an example of a 5 solar mass companion star that has the same brightness in the optical, and it has the same optical color too. So it will actually be really difficult to distinguish the two from just photometry in the optical. You can see a difference if you look at the ultraviolet, and this is actually the method that we decided to use, where we create a UV optical color to try and identify stripped stars. So for this to work, you really need to have an environment with low extinction and well-known distance, so that you can place these the stars on a color magnitude diagram. And something that has worked quite well for us is to look into the Magellanic Clouds. So this is a survey I started with Maria Drought. She's a great collaborator. She used to be a Hubble Fellow. Now she's a faculty at U Toronto. And her student, Bethany Ludwig. And we used this data set actually in the background. It's a Swift map of the Large Magellanic Cloud. And we combine the Swift data with optical data to try and find these stripped stars. What I will show today is primarily work that we just submitted a few weeks ago to Science, the discovery of the stripped stars, and also a little bit about the stellar properties, the parameters of stripped stars that we will submit in a few weeks. So this is actually data. So what we can see here is a UV brightness on the y-axis, and the UV blueness on the x-axis, and is for the large and the small Magellanic Cloud. So if we remind ourselves here, we need to find stars that have a bit more UV blueness compared to main sequence stars. So it should be objects that are blue wards of this 0H main sequence we can see here. For reference, these are some Wolf-Rayet stars in the Magellanic Clouds. And here are models of isolated stripped stars. They are usually not isolated, but just for reference to see how a really blue such object would look like. So this means that what we can see here, blue wards of the 0H main sequences, are candidate stripped stars. And we found in each of the clouds about 50 to 100 candidate stripped stars this way. And given their UV brightness, they probably have masses above 3 solar masses or so, but you need to look much closer at that. And taking some simple assumptions, you can infer what the total number would be, but I'm not going to go into detail on that today. So we decided to try and confirm that they indeed are strip stars by spectroscopic follow-up. So here you can see those color magnitude diagrams again, but the large circles now, they are spectroscopic targets. So we used the Magellan Bode telescope, the medium resolution MAGE spectrograph, and this is an ongoing survey where we now are monitoring the orbits of these stars, but it has started in 2019. And I want to acknowledge the great team that has helped with the observations. So apart from me and Maria, there is Bethany, and Anna O'Grady also helped us quite a bit with observations. So this is how the stars actually look like. You can see 3 different types here. This is what we found. For 2 of these types, you can see helium-2 lines. So that's an indication here of very high effective temperature. And you can actually also see some nitrogen-5 lines and nitrogen-4 lines in the top spectrum, which is an indication of even higher effective temperature. And in the middle and the bottom types, you can see signs of strong hydrogen lines, Balmer series lines, which is a signature typical to B-type stars or main sequence stars. So what we think that we see here is on the top a type of binary where the strip star is dominating the optical. In the bottom, we think that a B-type companion is dominating in the optical. And in the middle, we think that these are a double-line spectroscopic binaries where you see both components. And in fact, in a few of them, we have even enough spectra to confirm that hypothesis. So what I'm going to focus on now is to look into these strip stars that dominate the optical spectrum and show you what their properties may be like. So to do that, I had to develop a new grid of spectral models so that we can perform a spectral fitting on these stars. It was important to make a new one because there didn't exist any such model grid before, because we reach really high effective temperatures and really high surface gravities. So this model grid, it contains certain different range of hydrogen abundance too, because that's also something we want to measure. So then we fit the spectra to certain spectral lines that are sensitive to temperature, surface gravity, and effective temperature, and obtain measurements through chi-square fitting of these 3 parameters. You can see that the fit is relatively good. And then by adjusting this to the photometry, we can also obtain measurements for the bolometric luminosity, the extinction, using an extinction law for the Magellanic Clouds, and a radius of the star. And so you can see this particular star is small, it's less than a solar radius. And if we look now, something that I thought was interesting is the surface hydrogen mass fraction. Here you can see star number 7 that we have been looking at. It has about 0.35 mass fraction of hydrogen on the surface, so it's not completely hydrogen-free, but it is not at all like the main sequence stars that have about 0.7. And if you put the entire sample on this plot, you can see that there are stars that are completely hydrogen-free, and there are stars that are hydrogen-poor but not hydrogen-free. So I think that is really interesting, because that means that you can create, when these stars later explode, you can create both hydrogen-free supernovae and hydrogen-poor supernovae. And they also match the theoretical expectation of being in between these Wolf-Rayet stars and subdwarfs. So if we look here at the Hertzsprung-Russell diagram with temperature and bolometric luminosity, the sample ends up in between these stars. And if we also put on top here some evolutionary models of envelope stripping over here and contraction and helium core burning over here, you can see that these match very well with helium core burning strip stars, most of them with mass between 2 and 8 solar masses. So what does not match? Maybe we skip that one because I'm almost done. It's the winds. You can see the winds, yeah, different. What do we learn from this? We can see that the spectroscopic analysis shows that these stars are actually stripped stars. And we can learn some things about the evolutionary history and the final fate of these objects. First, we can see that stars actually can be stripped by low-mass stars or compact objects because that class where the stripped star dominates the optical spectrum, it exists. And envelope stripping can both leave some hydrogen or remove all hydrogen, creating that difference in the surface hydrogen mass fraction. And binary evolution models are actually relatively good at reproducing the properties of the stripped stars, apart from the wind mass loss that I didn't show you. For the final fate, most of these stripped stars would likely become neutron stars, given their mass. And they can produce both 1b and 2b supernovae. And then, given the wind, we can have some impact on binary neutron star formation. So for understanding the envelope stripping mechanism and the future orbital evolution, we need to need the orbital solutions, and that's actually what I'm working on at the moment. So hopefully I can show you that next time. But with that, thank you so much for your attention, and I'll be happy to answer your questions.
Thank you, Ilva. Do we have questions?
Hi, thanks for those good results. So based on the objects that you found in the Magellanic Cloud so far, and based on the range of helium fractions and hydrogen fractions that you're getting, do these results imply that there is not a single supernova 1C progenitor in the Magellanic Clouds, given that you're seeing helium in all of these things? Like, what would a 1C progenitor look like in the Magellanic Clouds? Would you be sensitive with your selection criteria to a 1C progenitor?
Hey, thank you for the question. Yes, we would be sensitive to 1C progenitors because 1C progenitors presumably do not have helium, and we see a bunch of helium in these stars. So none of these, I can say clearly, are 1C progenitors. They would need to lose a lot of helium to be 1C progenitors. It could be that later interaction can get rid of parts of the helium, but I do struggle with understanding exactly where the 1Cs come from. So it's a very good question, actually.
A quick one? Quick.
Since you had hi, Ilva, this is Mike. Nice talk. Since you had to glance over it, what do your observations tell you about the winds of these stripped stars?
Wow, thank you for the question. How kind. So here you can see the spectra of the stripped stars with both that dominate the optical spectrum. This is what I thought that they would look like. So this is my models from 2018, and the difference is that this is a really high wind mass loss rate. What actually matches is something that is more than an order of magnitude lower than is the standard wind mass loss rates of helium stars when you extrapolate. So there is a really big need to develop new theoretical models for the wind mass loss rates of stripped stars. And actually we have an ongoing HST program to try and measure better and maybe make an empirical model. But so far this is different, and what it can change is whether the star can lose that hydrogen that was in some of these stars, for example, and this means that it cannot. It can also give rise to more or less interaction. So if you have less wind mass loss, the star can swell further and interact more. So that way, perhaps we can lose more of the helium even. I don't know. It's interesting.
All right, let's thank Ilva again.
Oh. Nej, utan.
Hello? Yeah. All right. Well, thank you all so much. It's great to be here in person. It's the first conference I've had since the before times, and yeah, thanks so much to the leads. I'm going to talk today about stars off of the main sequence. I'm Melinda Soares-Furtado. I'm a Hubble postdoctoral fellow at the University of Wisconsin-Madison. So I'm very interested in objects both at very early times and at very late times in the stellar evolution. And that's because these are dynamically rich times where interactions are actually quite plausible. And I'm going to talk about both of those sort of early and late stages. But first, I kind of want to draw your attention to the current census demographics about known exoplanets. So while there's a wealth of planets, now well over 5,000 confirmed exoplanets, predominantly observed via the radial velocity and transit timing transit methods, the vast majority of them actually are about a very specific type of host, both in terms of the stellar mass and the evolutionary state. Here is an CMD just showing you the location of confirmed exoplanet hosts. Surface gravity is shown in the color bar there. We have one white dwarf object, that's 1856-534, which was recently discovered by a paper led by Andrew Vanderberg. But the vast majority lie along the main sequence, and this can be brought to your attention to be even more obvious when you just take a quick pie chart and separate objects by the surface gravity log g. Over 95% of them have surface gravities above 3.5 decs. And so our post-main sequence hosts are actually a small minority. And we can also compare by breaking this pie chart up into a histogram and see there's been a steady, increase of these post-main sequence hosts. Really no spikes with any sort of specific missions or discovery techniques, but hopefully that will change in the future. I also, before I start to show you some of the work that we've done, want to point out that in addition to it being a very specific type of evolutionary state, it's a very specific type of host mass as well. So in this histogram of host mass versus count of objects, you might not be able to see, but in red here, we have the post-main sequence hosts as well. The main sequence hosts are centered right about 1 solar mass. So these are sun-like main sequence stars. There's a slight offset, slightly more massive for the post-main sequence stars, and that makes sense because these objects evolve more quickly off the main sequence at earlier times. But still, that scatter here in this histogram is, between going up to about 3 solar masses. So for the wealth of orbital separations and planet masses, we have this incredible diversity in our exoplanet census demographics. But when it comes to the host stars, I think there's still a lot of work to be done. And what I want to compel you with in the next part of this talk is how interesting these late and early times are. It's also quite relevant to the current census demographics. So here on this plot on the right, where we have orbital distance in AU versus the surface gravity, I have on the bottom, we're showing the dwarf stars in that yellow panel. We have the post-main sequence turn-off objects there in the peach. And then overplotted atop this is the known demographics of our exoplanet, confirmed exoplanets. The lines there are actually showing you, with mesostellar models, how a host star will evolve as a function of time, and its surface gravity will change. And this is basically the radial size of that object. And so it makes sense that we don't see planets in this upper left-hand quadrant here because they would literally be inside their host stars. Remember, most of these host stars are about a solar mass. These models range between 1 and 1.8. But this is the fate that is awaiting some of these objects that are currently orbiting around main sequence stars. We know from many people who've given talks so far that these objects will expand in size and will, in many cases, engulf their host planets, their companion planets. And why should that matter? It might be interesting if you care from the perspective of the planet, most certainly, but I want to argue that it also matters from the perspective of the host star itself, that it can produce appreciable, long-standing observational signatures that impact that host star, despite the fact that the mass is quite lower. So some of those effects are optical UV and X-ray radiation spikes. I'll talk a little bit in a second about how much orbital energy is actually liberated in the engulfment process. You can also eject and strip the stellar envelope. This goes very well with what Ylva was talking about before, but now we have quite a different mass ratio. You can also produce changes in the angular momenta of the star, and that can be observed both by rotational enhancements and reductions. And maybe that's slightly counterintuitive when you first hear it, but it really depends on whether or not you have a prograde or retrograde planet. You can, in some cases, produce these near critical velocities in the host star. So these are not negligible effects. There are many cases where you can have not only rapidly rotating stars, but stars that are now unstable in terms of their own self-gravity. And chemical abundance anomalies can be induced. And so that's something I've also thought a lot about. So energy is liberated when, because of the orbital decay of the engulfed companion. There's still an open question about where this energy goes and what it does to the host star. It's quite a bit. I just want to show how much energy is liberated. So this was a paper led by Morgan McLeod, and we're looking at the CMD just here on the slide. And what we can see in the color bar is basically a ratio of the orbital decay energy that's liberated in a particular system compared to the intrinsic luminosity of the star. So we're thinking about the planet actually losing this energy in a few integer orbits and depositing that into the star. What it does, we really do not know, but how does it compare to that intrinsic luminosity? And what you see is actually if it's near that main sequence turnoff, it's pretty substantial. It can be a factor of 10,000 larger than the intrinsic luminosity. That's quite exciting that there's a lot of energy, but what is it doing? I think there's still a lot of work to be done to determine that. Ricardo Yarza, who's a graduate student at the University of California, Santa Cruz, thought a little bit about whether or not some of that energy that's being liberated might go into ejecting the envelope of the star. This is exciting work that was actually picked up by the New York Times last month. And in this plot, we're seeing the orbital separation of the star-planet system. We have our typical hot Jupiter zone here from 0.1 to 0.01 AU. And we have objects that are substellar companions down to about a Jupiter mass to a pretty massive object. And we see that we have these three distinct regions. We have objects that are making it all the way into the star but are destroyed in that convective envelope. We have objects that can make it quite a bit deeper. These are objects that tend to be denser and can survive that convective region and are not disassociated until they get below the envelope. And we actually have objects where the lever arm and mass are just right that you can eject the stellar envelope. You might expect some observational properties to accompany this, like infrared excess. So what you need for envelope ejection, you need a massive companion. So the substellar companion, the more mass, the better. And you want this long lever arm or a larger orbital separation, which means that the star needs to be at a more evolved state in terms of its evolution, later stages in the red giant branch. So for our post-main sequence turnoff, you were near the turnoff when you had a lot of that orbital energy that was liberated, but really for that energy to go into ejection, it needs to be at a much later time. So we also thought a little bit about how the planets can impact stellar spin and wanted to go out and find some of these objects. So this is work that I've done with one graduate student at the University of Minnesota, Tyler Barna. We've thought a little bit about open clusters and using open clusters to determine a pretty well-defined rotation sequence. So this is the Kepler magnitude or the mass versus the period. And typically stars they converge onto a nice rotational sequence. That rotational sequence gets tighter as a function of age. So you do expect there to be some dispersion about this, but you nicely can find these outliers as well that you can then follow up spectroscopically and see if they have chemical abundance anomalies that might be indicative of planetary engulfment. So this is something we've already done in M35 and NGC 2158, and we're currently doing with NGC 6791 and NGC 6819. We've also done some work just using mesostellar evolutionary models and Galah abundance surveys to try to determine if you basically deposited all of the lithium, let's think about lithium as being an interesting tracer here, into the convective envelope of a star, what is the statistical significance, what is the abundance signature, and what is the survival time for an object like that? This is a very idealized scenario where we just put everything in there, and in the best of situations, can you get a 5 sigma statistical significance in abundance? To do this, we used MESA to tell us how much mass was in the convective envelope, the temperatures at the base that could give us a sense of the survival time. But we really relied on Galah to get the abundance measurements just because it's nice to use this data-driven technique, and there's a wealth of data out there now in terms of photospheric abundance. And what we found is that there's a pileup that you would expect between 1.4 and 1.6 solar masses where you can get statistically significant lithium enhancement signatures that are also long-lived, and that was recently confirmed by a Lamask survey by Zhao in 2022 that showed indeed this pileup exists for these early evolved stars. So that was quite exciting. We're interested in other abundance enhancement tracers that could accompany lithium, because there are some ways that you also can be lithium enriched from other processes. However, near that main sequence turnoff, those processes are not very viable. So this is a very compelling lead. But what is the delta science about that? Why do we care so much about ingestion? I think I've talked a little bit about how it produces these stellar observables, and it can provide you a sense of the pathways and the progenitors that cause that. But it's also used for planetary reasons, in terms that it's one of the ways that you can directly measure the bulk composition of an exoplanet. So I think in tandem with white dwarf accretion, it's a really interesting pathway to explore. And this is particularly useful if you're looking in open clusters and co-moving groups, which is what we tend to do, because that's where you have the nice constraints, not only in the rotation, like I talked about, but also in your abundances. So anomalies are a little easier to spot. So that's what we're doing now. We're looking at the original Kepler data set, which is this wonderful long 4-year baseline. We're looking at NGC 6819 and 6791. I'm getting a lot of wonderful membership probabilities from Rachel McClure, who's a graduate student at the University of Wisconsin-Madison. And I'm also having Rihanna Kenzie work with us to do a lot of the classification, which we tend to do by eye. It's still sort of state of the art, in my opinion, to have several people look at all the light curves, if you can, if it is feasible and the numbers make sense. And here we're at numbers of about 10,000 light curves, which I think is doable. We're pairing that with test DDT data, because we have lots of interesting pulsational signatures in this data set. So if you're interested in pulsating blue stragglers or solar-like oscillators, we have tons of data there. And we also have 20 years of WIN open cluster survey data, and that's really helping us with deblending to determine whether or not some of these eclipsing binaries that are in large blended groups, which source is the primary and which is the secondary. Okay, I'm going to quickly wrap up. I'm seeing running out of time, but thinking about younger planets and stars, I'm very excited about the upcoming Roman survey that's launching in 2027. We've been doing some work to think about what would happen if we had a 30-day observation of the Orion nebula cluster and surrounding regions. There's been some wonderful work with Hubble survey treasury data that has looked at the number of free-floating planets in these regions. And we would be able to observe them because they're bright at 2 microns, and to monitor them for transits. So we could look for moons surrounding these objects, and we could also look for planets around brown dwarfs and planets around young M stars. So these are 1 to 3 million-year-old objects, and there's lots of open questions about the envelope capture, envelope dispersal, the orbital architectures, whether these objects are in resonance. And also you can do some kinematic investigations to say, for those free-floating planets, did they form in situ or were they ejected? And I think that would be an exciting thing to be able to do. So we've submitted 2 proposals so far. We are going to continue to work on this, but there's a paper coming out on the archive next week that will show you some of the yields predictions that would accompany this. Some of the things I'm most excited about, so we're looking at the host mass versus the detectable satellite radius down to a 7 sigma detection limit. There's a lot of unknowns about the sizes of these objects because, if you have a free-floating planet, does it have an extended hydrogen and helium envelope much longer if it didn't have that host star to radiate a lot of that material away? But what we know is we can get down to the radius of Titan for some of these systems. That's very exciting, specifically when you look at the known exoplanet population region, that we're really exploring a very different parameter space here. And I think that this is an exciting possible discovery survey. And here is just one of the best, my favorite plots of the moment. This is the host companion separation in AU. We have our traditional sort of 0.01 to 0.1 hot Jupiter regime, but we're looking at a wealth of host masses from the free-floating planets, the brown dwarfs, to the low-mass stars, and our typical sort of run-of-the-mill star that I've talked a lot about that's very well represented in census survey data. And we see that this extends down to, Ia, Europa, Ganymede, and Callisto, both in terms of the separation and in terms of the host mass. And it also is able to start to look at some of these proto-habitable worlds, so like early TRAPPIST-1 systems. So with that, I think we have much to learn from stellar hosts that are off of the main sequence, and that our census demographics are a little biased at the moment. They're exciting, and there's lots of beautiful discovery, but I'm also excited about the next chapter. Studying stars off of the main sequence will offer constraints and insights for both stellar astronomers and exoplanetary astronomers. And the exoplanet engulfment and ingestion can induce these observational anomalies in host stars that I think are quite interesting to study. And that in the future, I think we can look forward to space-based time domain infrared surveys that will tell us a lot more about these very young exoplanets and exosatellites. And thank you so much. I'll take questions.
All right, we have time for just one quick question.
Melinda, great talk. This is Mike Wong. I really love this idea of being able to probe bulk compositions of exoplanets using this method of watching for engulfment. For the case of a star engulfing multiple planets, say like, the sun engulfing Venus, Earth, Mars, Jupiter, can you disentangle the planets, or do you get a sort of smeared out picture of that solar system?
I think at the moment it's still pretty smeared. It's quite difficult, but even in a cluster, I think it's difficult to disentangle this. So. And lithium, as we saw, is really only something that you can use as a tracer for a very specific parameter space. It happens to be the main sequence turn-off mass for one of the clusters that we're looking at, so I think that's kind of helpful. And maybe the amount of lithium, we could back out how many Jupiter's masses worth of material you would have consumed. Outside of that realm, it gets a little more dicey, and so we're looking at what other tracers might be able to provide that sort of information. But thank you.
All right, let's thank Melinda again. Okay, our next speaker will be Mark Hahn from the University of Hawaii.
All right, can everyone hear me? Awesome. Hello, everyone. I'm Mark from the University of Hawaii, and my job is to survey red giants. More specifically, I survey the pulsations of red giants. Now, most, if not all, stars pulsate. And to do astroseismology, we monitor the pulsations of these stars to learn about their fundamental stellar properties and interior structure. Now, for red giants, like the sun and other solar-like stars, they have convective outer envelopes. And this convection stochastically excites acoustic pressure waves, standing waves that propagate throughout the stellar interior. And this causes the star to expand and contract, as you see in the very right panel. Now, how do we measure these pulsations? Of course, space telescopes. We have space photometers, transit hunting missions from Kepler K2 and TESS. These are looking for transits, but at the same time, they monitor stars for an extremely long amount of time, and this allows us to obtain light curves of many, many giants, many, many stars around the sky. And to do astroseismology, we take these light curves and we compute the Fourier transform. And these are two red giants that I've shown here, and I've computed their periodogram. And what we've shown here, circled, these are the oscillations for the red giant that we're interested in. It comprises typically of an envelope that modulates a series of peaks. Now, the central frequency of this envelope, well, a measurement we call nu max, this is the frequency at maximum power, and this tells us the surface gravity of the star. And this is related, therefore, to the mass and the radius. And if you zoom in even closer, you would see that each peak is labeled 0, 1, and 2. Now, the number 0, 1, and 2 here corresponds to the angular degree of the spherical harmonic of each oscillation mode. So this is a different type of standing wave that's being propagated within the stellar interior. And you also notice that this pattern repeats itself, 1, 2, 0, 1, 2, 0. And this is because what you're seeing are overtones. And if you measure the frequency difference between these overtones, like shown here, we get a quantity called delta nu. And this is related to the average sound speed of the star. And it tells you mean stellar density. Again, this is a quantity related to the mass and the radius of the star. So here you have some intuition on how seismology is able to tell us about the fundamental properties of the stars, field stars. And so because of this, we are also able to constrain the evolution of stars using seismology. Take, for instance, as a star evolves from the main sequence all the way up to the tip of the giant branch. the radius of the star will swell. And as you see here, the frequencies, the oscillation frequencies will shift to lower values, and they will also increase in amplitude. So this gives you an intuition of how seismology can constrain the evolution as well as the age of field stars. And in practice, we apply this through two methods. The first is using the so-called scaling relations, where we explicitly solve for mass and radius using the previous equations. And this typically gives us a mass precision of about 5 to 10% and a radius precision of about 3 to 5%. And this is for field stars, by the way, so this is remarkably precise. The second way is you take your seismology, you combine it with spectroscopy, photometry, you put it into your favorite modeling toolkit, and it gives you stellar ages as well. Now, this is not all that red giant seismology can do. In fact, there's so much that perhaps we need even a part 2 to talk about all that red giant seismology can infer about the stellar interior. My colleague Joel will talk a bit more about using these oscillation modes to infer about the interior properties of the star in the next talk. My talk will focus more about surveying red giants and inferring stellar parameters for thousands of red giants across the sky. So I'd like to begin this part by showing a cute little quote from the recent decadal survey. Astroseismology was a once bespoke method of sounding the internal state of the star. We have now measured the oscillations for thousands of red giants around the galaxy. We have observations from Kepler, which stared at a small patch of sky for a really long amount of time, 4 years. This long stare gave us exquisite astroseismic precision. So we have really good handles on the ages of these stars. Now, K2, which came after, stared at multiple parts along the ecliptic.
Apologies, I got a bit too vigorous there.
All right. K2 stared at multiple parts along the ecliptic, and because it stared at each patch of sky for only 3 months, the astroseismic precision was much less as expected. Now, you notice that we're only observing small parts of the galaxy. Can we actually observe the entire sky? What about the bright stars? And this is where we have a new player in the game. This is the TESS mission, which is NASA's latest transit hunter that stares across nearly the entire sky. And each color in this animation here is designed to show different observing sectors from TESS. And what you're seeing here is a near all sky coverage of the local galaxy from TESS's observations. And this is really remarkable. We have the largest sample of the local galaxy that's open to seismology to date. And what we've done so far is to apply machine learning and to sift through millions of light curves from TESS to detect oscillations in red giants. And from that, we have built up this mass map that you see below here. So at the top, this is the optical image from TESS. And on the bottom, this is a heat map comprising astroseismic masses from only 1 month of data from TESS. So if we look at this differently, what this mass map is telling us is that the plane of the galaxy is home to more massive stars on average compared to regions that are farther away from the galactic plane. More massive means younger stars, and of course, this is what we expect from the galactic plane. It's like our basic understanding of galactic structure, that the plane has more young stars in general. But again, I'd like to iterate that this is only based on 1 month of TESS data. This is the minimal amount of data that we obtain from TESS, and we're using astroseismology on. And already we can reveal such large structure in the galaxy. And this implies that the promise of galactic archaeology with astroseismology is really, really bright. No pun intended. But you might also wonder, TESS is probing such a small region around the galaxy. How much galactic archaeology can we really do? Well, the answer is actually quite a lot. If you were to look at the kinematics of the oscillating giants that have been probed by TESS, many of them show kinematics that are not indicative of just rotating within the galactic disk, rotating with the rest of the Milky Way. Many of these have high energy eccentric orbits, or some even move in retrograde orbits with respect to the rest of the Milky Way. And this is indicative of membership within the galactic halo. And this is naturally really exciting because it provides us the opportunity to measure masses and perhaps ages of stellar populations within the halo itself, which is something that we haven't really explored that much with previous transit missions. Now, I'd like to shift gears a bit and talk about precision astroseismology with TESS. Instead of just 1 month of data, let's try to do more with longer observations. And we really can achieve this with observations near the ecliptic poles. So these stars within these regions lie near the continuous viewing zones. So these have really long observations from TESS because of the overlap between sectors. Now, I've taken a look at some of the really nice bright stars near the ecliptic poles, and I produced this star map showing some of the naked eye stars within the ecliptic poles. Now, I've taken a look at some of the seismology of some very well-known stars like Brumium, like Beta Mensae, Alpha Reticuli, and some have really beautiful oscillations. And I'm so happy to look at this because naked eye stars, these are really well-known stars. And this has motivated me to construct the HD TESS catalog, the Henry Draper TESS overlap catalog. So these will be targets. These are oscillating giants within TESS's continuous viewing zones near the ecliptic that are also in the Henry Draper catalog, which is a bright to medium bright spectroscopic catalog. And the idea is to produce a sample of the best and the brightest from TESS. And so far, we have cataloged 1,700 bright oscillating giants, and we have measured their masses, radii, and evolutionary states. So these are ingredients that you require for stellar ages. And this endeavor is actually really helpful because many of these bright nearby stars have been involved in some part of a scientific study historically. I'd like to show this with my favorite plot. This is a popularity chart of all these bright stars as a function of magnitude. The popularity is measured by the number of references in SIMBAT, so the number of times the star has been involved in some study or the other. As expected, most of the bright stars are the most popular due to their proximity, but even as you plateau off, there is a scatter of some stars which are extremely interesting, intrinsically interesting because they have weird kinematics, peculiar chemistry, and now we have seismology. We have the masses, radii, and potentially ages for these stars. So what I'm getting here is that TESS is really allowing us to add another dimension of science to these really interesting stars. So I'd like to think moving forward here. I'd like to think about how we can move forward here and just say that I'm really excited with Gaia's latest data release because now it has produced astrophysical parameters for a really large volume of the galaxy around the sun. And I'm really hoping to correlate what we have learned from near all-sky astroseismology with all these additional parameters that is provided now by Gaia. And I believe we can do a lot in enriching the richest star map of the galaxy that is now provided by Gaia. So I'd like to conclude my talk here by just highlighting the two main points with TESS's legacy, really. It is the ability to perform near all-sky galactic archaeology that is informed with astroseismology for the first time. And the bright star synergy. We now have precise astroseismic parameters for a lot of really interesting bright targets, for which we have studied, involved in some chemical or RV study previously. And just the final word, TESS is still ongoing. I've made it sound as though it's stopped, but it's not. It's in cycle 5 now, and we're collecting more and more observations of the entire sky. So this would imply that as time goes on, we would be able to learn more and more, get a better astroseismic precision for a lot of the sky around us. So there is a lot to be optimistic about. And with that, I'd like to end my talk. Thank you for your attention.
All right. Thank you, Mark. We'll open it up for questions. Also, just want to extend that to online participants if there's any questions online as well.
Thanks, Mark. That's really cool. I was wondering if you look at all stars or you specifically target red giants. Like, what do you said at the beginning that all stars pulsate? Can you detect pulsations and get astroseismology from non-red giants?
Yeah, definitely. So the mass map that I've produced here, these primarily target red giants because all that I've talked about earlier about using scaling relations so and so, these mainly apply to solar-like stars, and because Soul-like stars, these are extensions of what we understand from the sun. Our intuition of measuring the properties of soul-like stars come from our intuition from the sun. So naturally, we can measure the masses in red-eye for these fairly well. But we can also measure pulsations for different kinds of stars. And presumably, with sufficient modeling work, also get masses and ages for those.
Great talk. So very exciting what Tess is doing, but it's still the baseline of Kepler is sort of unprecedented for a lot of astroseismology. I'm wondering what astroseismologists are looking forward to, what surveys or future instruments, or if there's really, room for us to start thinking about the development of something like that.
Great question. Well, I didn't really prepare much of a slide for this, but a few years ago, there has been simulation been conducted regarding the ability to do astroseismology of the galactic bulge with Roman. And it turns out that at least for a lot of stars that are within the clump, we would be able to measure oscillations somewhat comparable to the K2 mission for stars within the galactic bulge, which is naturally really exciting because the galactic bulge is such a dense field and it has a lot of stars at the same time. We predicted a yield of roughly 1 million stars. So even if you can do some rough estimate of seismic parameters there, it would be really insightful just to inform, what is the age of the bulge, for instance. So this one, we can talk more. There's a few more on my mind.
Question?
So for these red giants, where does the main uncertainty in your derived parameters come from? Does it have to do with metallicity or possible, I don't know, binarity or
all of the above? Yeah, it's a good question. There is perhaps Joel will address a bit about the uncertainty as well. But indeed, yeah, the modeling of red giants is still highly uncertain. There are quite some deficiencies with the input physics, our knowledge of the input physics that goes into modeling these giants as well. We talked briefly about, this scaling relations as well. So there is also some intrinsic uncertainty with using these scaling relations. Precise as it is, there are some parameter spaces, some stages of evolution where this scaling relation doesn't really hold up because our assumptions that go into these scaling relations, which is basically scaling off the sun's structure, it fails. So metallicity is one of these as well.
And presumably evolutionary stage and what?
Yes, evolutionary stage. And with the modeling, the input physics primarily.
All right. Thank you, Mark. Let's thank Mark again.
Mark, while Joel's getting set up, you had someone on YouTube said excellent talk.
Okay, our final talk before lunch will be from Joe Long.
Do I hide this toolbar? Okay. You all can hear me, yes? Okay. Hi, everyone. I'm Joe Long. I'm a starting Hubble Fellow at the University of Hawaii, and I want to talk to you today about rotation. So I hope it is not an overly controversial statement to say that essentially all stars rotate, and that an understanding of this rotation is essential to also understanding their origins, their operation, and their ultimate fates, right? But I should also point out that at present, almost all of our means by which we characterize this rotation is evaluated at the stellar surface. So allow me to be a bit more precise. In living as we do in this era of precise space-based photometry, it's typical that we analyze this time series photometry in the frequency domain. And if we had access to God's own photometer, we would be able to, analyze this time series in the petahertz regime, at which point you're basically taking spectra of the star, and from this you'd be measuring a spectroscopic rotation or broadening, which is at the photosphere. If you are lucky, your star will have spots, and you can then also measure the rotation rate as spots rotate into and out of view. Again, that's at the stellar surface. But if you are extra lucky, then your star will exhibit this kind of phenomenology in the frequency domain. And as Mark has helpfully explained for me, this corresponds to what you would see in a solar-like oscillator, where each of these peaks is a single resonant mode the single resonant mode of oscillation for a pressure wave or a P mode. And these P modes are characterized by a characteristic spacing, delta nu, between successive overtones, as well as an overall envelope centralized at a resonant frequency nu max. And that's basically all you need if the only thing you care about is the stellar mass and stellar radius. But if you want to peer into the inside of the star, for example, to study its rotation, then you need to also consider the frequencies of each of these individual modes of oscillation. To do so, I will rearrange this figure to make it easier to reason about these frequencies. First, I will break the power spectrum down into chunks of equal size delta nu, and I will layer these chunks in increasing order of frequency. In this representation, the power spectrum appears to have some kind of three-dimensional structure, which, takes the form of a bunch of ridges, right? And the shape of these ridges tells you about the structure of the star, but that's a different talk. Today, I want to only focus on the fact that each of these ridges can be seen to exhibit modes of different multiplicities, right? So this ridge is composed of single peaks, this one of double peaks, this one of triple peaks, and so forth. This is the basis of us assigning to each ridge a different angular degree L, because, the pulsations occur based on spherical harmonics, and each spherical harmonic can be described by a quantum number L, right? So the reason for this is that if you have a pulsation or rotational axis, depending on the degree L, you have different possible solutions to the wave equation, some of which propagate in a prograde fashion relative to the axis, and some in a retrograde fashion. In the presence of rotation, those modes which oscillate in a prograde fashion will be seen by a stationary observer to execute their pulsations more rapidly than the retrograde ones, which in turn appear to slow down. The inclination of the rotational or pulsational axis then also determines which of these modes appear to cancel out over the visible disk more or less. The observational consequences of this are that to a stationary observer, the presence of stellar rotation causes each of these modes to split into an apparent multiplet in the power spectrum, right? With the degree of the mode specifying the number of components in the rotationally split multiplet, and the inclination determining the distribution of power between the components of the multiplet. So this would be a sufficient description of the phenomenology of main sequence rotating solar-like oscillators. But unfortunately, the majority of stars that we have in our observational sample are not main sequence stars. It is instead dominated by evolved stars whose observational morphologies require a few more moving parts to fully describe. Here I show the evolution of a similar diagram for a series of stellar models crossing the Hertzsprung gap and ascending the red giant branch. So the more or less vertical morphologies of the diagram, which is typical of main sequence stars, can be seen to be disrupted by an extraneous set of modes which interact with the existing P modes in a rather complicated and nonlinear fashion. You can also see that these interactions and evolution of this diagram becomes increasingly rapid as the star ascends the red giant branch. And this causes the modeling to be quite a bit more complicated. So what's actually going on here is that each of these extraneous modes corresponds to the resonant frequency of an internal gravity wave, a G mode. And these G modes are confined to the stellar interior, and so they can be to an observer like us, they are seen with much narrower line widths and much lower amplitudes than that of pure P modes. Over the course of stellar evolution, the frequencies of the G modes increase and the frequencies of the P modes decrease. And if that were all that were happening, then what we should be seeing is that the two modes should just cross in the power spectrum like so. But that's not what's actually happening in these evolved stars. Rather, the two mode cavities are coupled together in an evanescent fashion, right? And so over the course of stellar evolution, what happens is that the G modes and P modes interchange characters smoothly and avoid each other rather than crossing. So what we are mostly seeing in these evolved stars are mixed modes of intermediate character between P and G modes. And it is this mode mixing that causes complications when attempting to determine stellar rotation in an interior. Come on. Okay. So, in general, for any mode, the amount by which it is rotationally split depends to leading order in perturbation theory on an integral of the rotational profile against some sensitivity kernel associated with that mode. Here, I show the integrated sensitivity kernels associated with a pure P mode, which is in gray, and a pure G mode, which is in red, right? So in an evolved star, the G modes are confined essentially entirely to the radiative interior, which shrinks as the star ascends the red giant branch, while the P modes are confined to the convective exterior, which become increasingly distended for red giant stars. Consequently, for these stars, the amount of rotational splitting that should be experienced by a pure P mode is quite small, and the amount of rotational splitting that is experienced by a pure G mode is quite large. So the angles are small and large on this diagram. And then you would expect, therefore, that a mode of intermediate character should be likewise split by an intermediate amount. But that's not what actually happens. Rather, the actual rotational splittings experienced by the mixed modes appear to exhibit a family of avoided crossings, one family for each M. And this causes the inference of rotation rates for mixed modes to be rather complicated. So for this reason, our ability to measure rotation rates for these evolved stars is primarily confined to the radiative core. And in particular, because these avoided crossings become most significant in the neighborhood of the P-dominated mixed modes, we have considerable difficulty constraining simultaneously both core and the envelope rotation rates in these evolved stars. Okay, so to move forward with this problem, we note that similar issues were encountered in the early days of quantum mechanics when people were still figuring out, how molecules and atoms work. And in an earlier paper, which I wrote with my advisor a couple of years ago, we basically transplanted the solution that the pioneers of quantum mechanics developed back then to the situation in natural seismology. And in the paper which we have now under review, we've generalized this construction to also include now rotational effects. So using this new construction, we are able to go back from the observed sets of mixed mode rotational splittings to the implied splittings associated with the underlying pure P and pure G modes. With these symmetrized splittings in hand, we're now able to also then apply techniques that were originally developed for helioseismology. In particular, since the sensitivity kernels of different modes sample different parts of the star, we may judiciously combine them in such a fashion as to effectively cancel out the sensitivity everywhere in the star except for a pre-selected localization radius, right? Correspondingly, the associated linear combination of rotational splittings then will tend to a localized estimate of the rotational profile at that part of the star. And so these techniques were initially developed for helioseismology, but in the same paper which we have now, we've also shown that the associated pure P and pure G mode rotational splittings that we infer from our procedure may be used in a similar inversion procedure to estimate localized rotation rates for evolved stars. And so this is just the culmination of a long-standing effort that we've had in order to attempt to generalize helioseismic techniques to evolved stars. And we are now then in a position to apply them to an actual testbed. For this purpose, we've selected a Kepler star, which for the shell diagram of which I show here. And we've selected this star for some rather unusual rotational properties, in particular that its spectroscopic rotational velocity is really high, and we have no idea why. And so we've decided that this is the ideal situation in which we would want to test this new technique. So that's really the starting point of my fellowship, and I hope to be able to report new interesting results next year. Perhaps not just for the star, but for an expanded sample, and perhaps even like further physical consequences. Okay, so that's really all I have for you today. I'll leave you with my summary slide, and I'll be happy to take questions. Thank you for your attention.
Thank you, Joel. Questions?
I was really happy when I saw the last slide because I was thinking about non-monotonic rotation a little bit. I'm wondering how that complicates things and where maybe the technique might have some limitations, or can you just expand a little bit about what you might be able to provide for a non-monotonically rotating star?
Okay. The main difficulty with non-monotonic rotation is that it violates a lot of assumptions used in the current techniques by which we measure, or attempt to constrain envelope rotation. And in principle, the inversion procedure I'm describing is independent of our model of what rotation looks like. It only depends on our model of the structure rather than the dynamics of the star. So in principle, this technique is way better suited to characterizing non-monotonic rotation in the stellar profile than existing techniques of differential rotation.
Thanks, Joel. That's really cool. How does it compare to what Mark showed before about, like, is it specific that you can disentangle the rotation and the pulsation in the frequency signature?
I'm not sure what you mean. So what Mark was describing was using essentially only the global properties of the oscillation. So basically, when you look at the power spectrum, you see this comb structure. And what Mark is using is only the average spacing between overtones for determining the properties of the star. What I'm doing here is I'm using all the mode frequencies individually to constrain the structure of the star, that is the insides rather than the mass and radius, and then using that as a starting point for also constraining the differential rotation within the star. So it's like the global properties versus interior structure.
But wouldn't the pulsation also violate some of your assumptions?
Yes. But as long as our constraint of the structure is good enough, then that's not a problem. So a similar issue arises in helioseismology, where even our best standard solar models don't quite reproduce the structure of the sun. But as long as we have a close enough guess, we can, essentially back out the differences in the structure and then the dynamics of the star.
All right. Do we have any questions online? No? All right. Well, we can thank Joel and all the speakers from this session again.
So we reconvene at 2:15.